Greetings of the day to all of you. Today we'll try to solve a couple of numerical problems based on last lecture, that's lecture number 19 part A. Let me remind you, lecture number 19 part A was discussions and analysis of three-phase unbalanced non-sinusoidal system. There we got the mathematical expressions for average powers of all the three phases, total average or active power, reactive power of individual phases and total reactive power, then vector apparent power, arithmetic apparent power, and effective apparent power, and the respective power factors. Now, based on those discussions and to make things clear, we are going to take a couple of numerical examples. Let us solve these examples. We'll first of all go for example number 1. Okay, this is example number 1. We will try to solve this example 1. The example 1 is written on the paper here. It's written that for a three-phase system shown below. I will draw the three-phase system in a moment. VA, VB, and VC are balanced sinusoids with RMS value of 220 volts. The feeder impedance is RF plus JXF equal to 0.02 plus J01 ohm. The unbalanced load parameters are RL equal to 12 ohms and XL equal to 13 ohms. Compute the following. Part A, currents in each phase, that's IA, IB, and IC, and neutral current IN. Part B, losses in the system. Part C, active and reactive powers in each phase and total three-phase active and reactive powers. And Part D, vector apparent power, arithmetic apparent power, and effective apparent power and power factors based on them. Let us first of all draw the circuit diagram of this three-phase unbalanced system. So the circuit diagram is like this. Let me complete the circuit diagram first. These are feeder impedances. This is phase voltage or phase to neutral voltage VA. This is phase voltage VB. This is phase voltage VC, and this is neutral voltage VN. Okay, and this is our load. L and C, L and R. This is the load. Load is connected in a very peculiar way. I mean, these are your three lines, line A, line B, line C, along with neutral. This is a three-phase, four-wire system along with the neutral wire, but load is not connected to equally in all the three phases. It is connected something like this. This inductance is connected here between lines A and B, and a resistance L is connected, resistance R is connected between phase C and neutral. Okay, the feeder resistance is RF, and feeder reactive inductive reactance is JXF in all the lines. RF, JXF, RF, JXF, RF, JXF. The voltage of phase A is VA. This is the phasor, voltage phasor VA. Of course, it is voltage between phase and neutral, phase to neutral voltage, or we can call it phase voltage. This is voltage phasor VB. This is voltage phasor VC, and this is voltage neutral voltage phasor VN. And the line currents are, this is IA. Okay, line current phasor IA. This is line current phasor IB. This is line current phasor IC, and this is the phasor neutral current phasor IN. Okay, so this is I will write here, unbalanced three-phase system. There are no harmonics in this system. The voltage is balanced. I mean, the three-phase voltages are balanced. It is given in the problem that the supply voltage has an RMS value of 220 volts. All phase voltages are 220 volts. That means phase voltage VA is 220 at an angle of 0 degree volts. Phase voltage VB is 220 at an angle of minus 120 degrees volts. And phasor VC is equal to 220 at an angle of plus 120 degrees volts. So this is a set of three-phase balanced voltages. The voltages are balanced. Voltages are not unbalanced. But load is unbalanced. Okay, the load reactance is given, XL load reactance is given in the problem. It's given as how much? It is 13 ohms, and load resistance RL is given as 12 ohms. An inductive reactance of 13 ohms an inductor is connected between lines A and B, and a resistance of 12 ohms is connected between lines C and neutral N. So this makes currents in these line currents IA, IB, IC unbalanced. And as soon as there is unbalance in the currents, that will result in the flow of neutral current. See, this is a sinusoidal three-phase system. It is written for us three-phase sinusoid. VA, VB, and VC are balanced sinusoids. So there are no harmonics. Okay, had the system been balanced, the neutral current would also have been zero because the voltages and currents are sinusoids. But because of unbalance in the load, the unbalanced currents IA, IB, IC will flow, and that will result, this unbalance will result in the flow of neutral current. So we have to find all that. In part A, we are asked to find currents in all the three phases. We have to find current IA, current IB, and current IC, and also neutral current IN. So this is what we are supposed to find in part A. Let us try to solve it one by one. Now we know that let us go for the solution. This line current IA is equal to VA, phase voltage VA by, okay. See, I want to find this line current IA, okay. My load is an inductance with inductive reactance XL equal to 13 ohms. And you can see this inductance is connected between the two lines, two phases VA and VB. So therefore it does not receive phase voltage, it receives rather line voltage because it is connected between the two lines. So therefore what is the voltage across this load inductance XL? It is line voltage VAB. Okay, so VAB, let us first of all write, or let me write here that this current, line current IA, will be equal to voltage across the load, which is not phase voltage but which is line voltage, VAB by XL, because load is inductive reactance, XL 13 ohms. So therefore we have to find line voltage, a magnitude RMS value of line voltage VAB, because VA is given to us, VB is also given to us, phase voltages are given to us. Now we can find line voltage VAB. So what is VAB, by the way? It is VA minus VB, and VA is already given to us. It's 220 volts, of course at an angle of 0 degree, minus VB is 220 volts at an angle of minus 120 degrees. So that means VAB is equal to, this is 220, if I take 220 out, okay, so this will be cos 0 plus j sin 0. Cos 0 is 1 and sin 0 is 0, so it will be into 1. Minus here we have again 220 cos of minus 120 degrees plus j sine of minus 120 degrees. Okay, so we can solve it. So therefore line voltage VAB will be equal to, this is 220 into 1 is 220 minus 220 into, what is cos of minus 120 degrees? Cos of minus 120 degrees is minus 1 by 2. This is 220 here. So it is minus 1 by 2 plus j sine of minus 120 degrees. So what is sine of 120 degrees? It is root 3 by 2. So it is sine of minus 120 degrees. So that is minus j root 3 by 2. So therefore the line voltage VAB will be equal to 220, okay. Minus into minus is plus, 220 by 2 is 110, minus into minus is plus, j 110 root 3, okay. So that means line voltage VAB is equal to 220 plus 110 is 330 volts. This is the real part, and imaginary part is J 110 root 3 volts. Okay, so if you find the magnitude of this voltage, amplitude, RMS value, that is under root of 330, under root of real part square plus imaginary part square, 330 square plus 110 root 3 whole square. Okay, so solution or computation of this gives line voltage, RMS value of line voltage as, so let me give you the RMS value of line voltage. It is 381 and it is at an angle of 30 degrees volts. Why 30 degrees angle? Because this phase angle phi is tan inverse reactive part by real part. Imaginary part is 110 root 3 divided by real part is 330. So if you find tan inverse of imaginary part by real part, that gives 30 degrees. Okay, that's what I have written here. And this comes out to be equal to 381 volts. So this is your VAB. So therefore, what is your line current IA? So therefore, line current IA is VAB by XL. VAB is 381 at an angle of 30 degrees by what is XL? XL is 13 ohms, but it is at an angle of 90 degrees. Okay, because what is your load? Load is purely inductive, and in case of inductive, we already know that inductive reactance is written as, say for example, it is 13 ohms and its angle is 90 degrees, because in an inductance current lags behind the voltage by 90 degrees. So when you solve this, this will give you the phase current IA. So that phase current IA will be 380 by 13 is 29.3 amperes at an angle of, say, 13. This will be at an angle of 30 minus 90, because this 90 will go up, it will be 30 minus 90, that is minus 60 degrees. This is line current IA. So therefore this line A will carry a current of 29.3 amperes. The RMS value of current IA flowing in this line, that is line current IA, will be 29.3 amps, and it is at an angle of minus 60 degrees. Okay, so once we have found IA, it will be very easy for us to find the other currents. What is IB? IB is same as IA, but it is minus of IA, because when IA is flowing, for example, in this direction, IB will be in this direction. Current coming like this and going like this. So therefore, line current IB will be minus IA. So that gives my line, that gives me the line current equal to minus 29.3 at an angle of minus 60 degrees amps. So this is my IB. Okay, so that means my IB is same as IA. Now I have to find IC. IC is current flowing in this line. Now this line, in this line you have a load resistance of load which is resistive in nature of ohmic value 12 ohms. And you can see this load is connected between phase and neutral. So which voltage will get applied across the load? It is not line to line voltage, it is line to neutral voltage, VC. So therefore, line current IC will be equal to VC by R. Because what is VC? VC is phase to neutral voltage. Because your resistance, load resistance is connected between phase and neutral. So it will receive phase to neutral voltage, VC. And what is VC? VC is 220 at an angle of plus 120 degrees by R. R is 12 ohms. 12 ohms resistance is at an angle of 0 degree. So that will give you line current IC, and that comes out to be 18.33 at an angle of plus 120 degrees amps. So this is line current IC. So this is line current IC, and same current is flowing through the neutral, because the resistance, load resistance is connected between line and neutral. Same current will flow in series with the neutral. So therefore, what will be neutral current? That is minus IC, that is equal to minus 18.33 at an angle of 120 degrees amps. So therefore, we have got all the currents. We have got IA, line current IA as 29.3 amps at an angle of minus 60 degrees. Line current IB is same but opposite, minus 29.3 at an angle of minus 60 degree amps. Line current IC is 18.33 at an angle of plus 120 degrees amps, and neutral current is minus 18.33 at an angle of 120 degree amps. So that completes our part A. So from this part A, it is very much clear that the system becomes unbalanced. All the source voltages are balanced, having RMS value of 220 volts each and having a phase shift of plus minus 120 degrees. So supply system is balanced, but load currents become unbalanced by virtue of connection of loads in this manner. Our line current IA is 29.3 amps. B is also same 29.3 amps, but C line current IC is 18.33 amps. So it is not equal to IB. And this gives us a neutral current of 18.33 amps. So that completes part A of this problem. What is part B of the problem? In part B, we are asked to calculate losses in the system. So we have to calculate losses in the system. Now my question is, where are losses in the system? Losses are in the resistances of the lines. You have three lines, 1, 2, 3 and neutral. So each line and neutral, that means all the four wires have a resistance of 0.02 ohms, because it is given in the problem that RF plus JXF. How much is this? It is given in the problem. Let me write it. 0.02 plus J is 0.1 ohm. That means line resistance of each line is 0.02 ohm and line reactance of each line is 0.1 ohm. So therefore losses in the line or feeder losses, there will be feeder losses in the line, and these feeder losses will be equal to IA square. What is current flowing in feeder A? IA. Because copper loss is I square R. So IA square plus what is current flowing in line B? It is IB square plus what is current flowing in line C? It is IC square plus what is current flowing in line this neutral wire? It is IN. So IN square into RF, because each line has a resistance of RF. So it becomes our copper loss, I square R. So copper loss in line A is IA square RF, in line B, IB square RF, in line C, IC square RF, and in neutral wire, it is IN square RF. So total copper loss in all the four wires, or total feeder loss, is IA square plus IB square plus IC square plus IN square into RF. So that gives us, what is IA? Just few moments back, we have found RMS value of phase current IA. It is 29.3 square here, plus IB is minus 29.3 square, plus IC is 18.33 square, plus neutral current is minus 18.33 square into RF. What is feeder resistance of each line? 0.02 ohm. So when you compute this will give you the line losses or feeder losses equal to, I have already calculated them. You please verify. It is, as per my calculations, this comes out to be 47.8 watts. So this is the total loss taking place in the system. See, if the system would have been balanced, I mean load also would have been balanced, the neutral current would have been zero. Then this IN square RF would not have been there. But because of unbalance in the load currents or unbalance in the line currents, neutral current of 18.33 amperes is also flowing. So that gives an additional neutral loss. And therefore total line losses in line A, line B, line C, including neutral, the total line losses are 47.8 watts. Okay, so that was about part B of the problem. Let us try to solve part C of the problem. What is part C? Part C says you have to find active and reactive powers in each phase and total three-phase active and reactive powers. Now you have to find active and reactive power of each phase. Part C. All right, here you have to find active and reactive powers in each phase and total three-phase active and reactive powers. Total three-phase active and reactive powers. we have to calculate these. First, we have to find active power carried by each phase, then reactive power carried by each phase, and then total three-phase active power and total three-phase reactive power. Let us start with phase A. What is the, by the way, what is apparent power carried by phase A? I will write here phase A apparent power. Phase A apparent power. Phase A apparent power. It is given by SA. That is simply phase A voltage multiplied by phase A or line A current, but complex conjugate. We already know apparent power is given by V into I, the star, voltage into complex conjugate of current. So that's what I am writing. So what is, by the way, voltage? We already know voltage, VA is VA into I. So VA is 220 at an angle of 0 degree into what is IA? Just few moments back we found IA, and if you remember IA we found as 29.3 at an angle of minus 60 degree amps. So it will be IA will be 29.3, but when you take complex conjugate, this is minus 60 degrees, this will automatically become plus 60 degrees. Complex conjugate of IA, which is 29.3 at an angle of minus 60 degree amps, it will become 29.3 at an angle of plus 60 degree amps. Okay, so this minus 60 degree phase angle with, when you apply complex conjugate, will become plus 60 degree. So if you solve this, this comes out to be 6446 at an angle of plus 60 degrees, because this is 0, 0 plus 60 is 60 degrees. Okay, that is equal to 6446 cos 60 degrees plus j sine 60 degrees. That is 6446 cos 60 degrees is 1 by 2 plus j sine 60 degrees is j root 3 by 2. So therefore SA will come out to be 3223 plus j 5369.5. Okay, so this has a real part and this has imaginary part. This real part is the power and imaginary part, the active power. Real part is the active power and imaginary part is the reactive power. So therefore active power carried by phase A, PA, is 3223 watts, and reactive power carried by phase A is 5369.5 watts. Okay, and how much is the apparent power? This is 6446 VA. We have already found that. That is this 6446. So apparent power carried by phase A 6446 VA, out of which active power carried by phase A is 3223 watts. Reactive power carried by phase A is 5369.5 watts. Okay, fine. That is about phase A. Now let us try to find apparent power, active power and reactive powers of phase B. Let's quickly move to phase B. Now, what is apparent power of phase B? It is VB into IB star. That is voltage phasor into voltage into complex conjugate of current. If you remember, voltage is 220 volts at an angle of minus 120 degrees. And current, just few moments back you have found, how much is current? It is 29.3. There it is minus 60 degrees. Here complex conjugate will make it plus 60 degrees. Okay, so that will come out to be, so it's a similar equation. So this is 220 at an angle of, so this will become 220 into 29.3. What is 220 into 29.3? Same, 6446 at an angle of this is 60, this is minus 120, so minus 120 plus 60 is minus 60 degrees. So that will come out to be 6446 times cos of minus 60 degrees plus j sine of minus 60 degrees. So that is equal to 6446 cos, this is 1 by 2, okay, sine of minus 60 degrees minus j root 3 by 2. So that will give SB equal to 3223 minus J 5369.5 69.5. Okay, so therefore active power carried by phase B is 3223 watts, and reactive power of phase B, QB, is 5369.5 watts. This is same as phase A because same amount of current is flowing in phase B also. So apparent power of phase B is this 6446 VA. Okay, so that is about phase B. What about phase C? Very quickly we will go for apparent power of phase C. Apparent power of phase C is voltage into complex conjugate of current. Voltage of phase C is, phase C voltage is 220 at an angle of plus 120 degrees into how much was current in phase C. We have calculated few minutes back, it's 18.33 amperes, and there it was at an angle of plus 120 degrees. If you remember, just few moments back, we have calculated IC. IC was 18.33 at an angle of plus 120 degree amps. But when you take complex conjugate of this plus 120 will become minus 120 degrees. So therefore, this will become 220 into 18.33. How much is that? That will come out to be 4032 at an angle of plus 120 minus 120 is 0. So that will come out to be 4032 plus J0. That means phase C is carrying only active power, no reactive power, and that is true also because there is no inductance connected here. So therefore, what is active power of phase C? It is 4032 watts. Reactive power of phase C is 0 watt. And apparent power of phase C is same as active power, 4032 VA. So that was about phase C. So therefore we have calculated all the three phases. In all the three phases we have found active powers, reactive powers as well as apparent powers. So therefore individual active and reactive powers, in individual phases separately we have found. So therefore what is total active power? Total three-phase active power. Let us call that P three-phase. That is equal to PA plus PB plus PC. And P three-phase is equal to, that will come out to be 4032 watts because phase A carries some active power, phase B also carries some active power. But those powers, they will cancel because what is between phase and phase B, phase A and phase B, you have pure inductance. Okay, although in the calculations you have found that there is some active power flowing in phase A, but there will be equal and opposite active power flowing in phase B, so they will cancel out each other. So therefore, if you have to find what is the total active power in this phase A, that will be PA minus PB. So that will cancel out, and then you are left with only phase C. And what is the active power carried by phase C? Just few moments back we have found active power carried by phase C is 4032 watts. It carries only active power, no reactive power. So this is total three-phase active power. Similarly, what is total three-phase reactive power? Total three-phase reactive power, Q three-phase, is equal to reactive power of phase A plus reactive power of phase B plus reactive power of phase C. That is equal to, what is reactive power of phase A? 5369.5 plus what is the reactive power of phase B? This is also 5369.5. Phase B also carries same amount of reactive power. And what is the reactive power carried by phase C? Phase C does not carry any reactive power. Just few moments back we have found that. So that will give you total three-phase reactive power, and total three-phase reactive power comes out to be 10,739 watts. Okay, so that completes our part. Which part was this? This was part C, active and reactive powers in each phase, and total three-phase active and reactive powers. And now in part D, you have to find vector apparent power, arithmetic apparent power, and effective apparent power. and power factors based on them. Last part, you have to find vector apparent power, arithmetic apparent power, effective apparent power, vector power factor, arithmetic power factor, and effective power factor. You have to find all this. Let us first of all find vector apparent power. Vector apparent power is under root of p square plus q square. And just few moments back you have found what is the total active power. Total active power is 4032 whole square plus what is total reactive power? It is 10,739 whole square. So that will give you vector apparent power, and this comes out to be, if you take square of these square root of these squares, this comes out to be 11,471 VA volt ampere. This is the vector apparent power. Okay. Then what is arithmetic apparent power? Arithmetic apparent power is this. It is SA plus SB plus SC. And what is SA? Individual apparent powers we have already found. By the way, what is SA? SA is 6446. 6446 plus SB is also 6446 and SC is 4032. We have few moments back found it. That will give you arithmetic apparent power, and this will come out to be 16,924 VA. Now you can see arithmetic apparent power is higher than vector apparent power. It's because of the fact that your system is unbalanced. And when your system becomes unbalanced, I have already told you, the feeder losses increase. You have large feeder losses like 47 to 48 watt power losses are there in the feeder. Okay, if the system was balanced, then feeder losses would have been less, but because of unbalanced system, the feeder loss is higher, and that increased feeder loss is taken care of by this type of apparent power, that's arithmetic apparent power. So arithmetic apparent power is 16,924 VA, whereas vector apparent power is only 11,471 VA. So arithmetic apparent power is higher than vector apparent power because it takes care of unbalance in the system, and hence unbalanced, increased losses because of this unbalance, right? And now we have to find effective apparent power. Effective apparent power, if you remember, it is 3 times VE into IE. Now let us try to find VE first and then IE. Now what is VE? We already know it is under root of VE1 square plus VEH square. H is the harmonic. Since our three-phase system is purely sinusoidal system, it is given in the problem itself. So VEH is equal to 0. So therefore VE is equal to under root of VE square, VE1 square itself. And what is VE1 square? It is VA square plus VB square plus VC square by 3. And all the three voltages, VA, VB, VC are 220 volts each. And that means it is under root of 3, let us call this V, each voltage V, 3V square by 3, 3 and 3 goes, so it is V. So VE is equal to V, that is equal to 220 volts, because it is a balanced three-phase system. I mean, source voltages are balanced. So effective voltage will be same as RMS value of phase voltage, that's 220 volts. Now what about currents? Now your effective current will be under root of IE1 square plus IEH square. Since there are no harmonics, these are loads are linear loads. So no harmonics are there in the currents. So IEH is equal to 0. So therefore my effective current is under root of IE1 square. If you remember, this IE1 square is IA square plus IB square plus IC square plus IN square by 3. And what is IA square? IA is 29.3 whole square plus IB is minus 29.3 whole square plus IC is 18.33 whole square plus neutral current is also 18.33 but minus 18.33 but square by 3. So that will give you IE and effective current, and that comes out to be 28.21 amperes as per my calculations. I advise all of you to verify these figures, check these figures. So therefore, effective apparent power will be 3 VE IE. So that is equal to 3 into VE is 220 volts to IE, just few moments back we have found 28.21 amps. So that will give effective apparent power, and it comes out to be 18,624.5 VA. And this is highest of all. Okay. A minute back you have found, you just 1 minute back you found vector apparent power, and that vector apparent power was how much? That was only 11,400. Vector apparent power was 11,471 VA. You also found arithmetic apparent power, that was how much? 16,924 VA. And now we have found effective apparent power. It is 18,624.5 VA, it's highest of all. Why is effective apparent power higher than all? Because this effective apparent power takes care of the additional power which is flowing in the neutral. Vector apparent power does not take care of unbalance. Vector apparent power does not take into consideration the neutral power carried by the neutral wire. It takes care of only three, power in the three phases. Then arithmetic apparent power takes care of power carried by three phases and also additional loss, increased feeder loss because of unbalance in the system. But this vector apparent power also does not consider additional power flowing in the neutral. It is the effective apparent power which takes care of everything. It takes care of power carried by all the three phases. It takes care of unbalance in the system which causes additional feeder losses, and it also considers the additional power which is carried by the neutral conductor. That's why effective apparent power becomes highest of all. It's 18,624.5 VA. So based on these apparent powers, you can now find various power factors. Like you can find vector apparent power, it is P by SV. And how much is P? Total three-phase power. Total three-phase power is 4,032 by SV. SV is vector apparent power, 11,471. And if you find vector apparent power, as per my calculation, it comes out to be 0.352. Power factor is very poor because you have a very strong inductance here, 13 ohms inductance connected between lines A and B. Okay, that's why power factor is as low as 0.352. What about arithmetic power factor? Arithmetic power factor is P by SA, where SA is the arithmetic apparent power. That is 4,032 by SA is 16,924. So arithmetic power factor will come out to be even less, 0.238. Comes out to be 0.238. It is even less than vector power factor. Why? Because arithmetic apparent power is higher than vector apparent power. So this power factor is less than vector power factor because it considers additional power loss in the feeders due to unbalance in the system. And finally, effective power factor is real power, total three-phase real power by effective apparent power. That is 4,032 by what is effective apparent power? 18,624.5. So effective power factor as per my calculation is 0.216. So it is even less than arithmetic power factor, slightly less than this because it takes care of additional power carried by the neutral, which is not taken care of by these power factors. So therefore, from this analysis, we have found that the system is unbalanced and as well as neutral also carries the power. So therefore, effective apparent power is greater than arithmetic apparent power, greater than vector apparent power. And effective power factor is less than arithmetic power factor, less than vector power factor. So I hope this problem has made whatever we have studied and analyzed in the previous lecture, lecture 19 part A, three-phase unbalanced non-sinusoidal system, although we have not taken care these unbalanced, this harmonics into consideration here, but at least it has given you an idea of a difference between vector apparent power, arithmetic apparent power, and effective apparent power. It takes care, in this problem we have calculated all the three type of powers, apparent powers, and all the three types of power factors. Because our system was unbalanced, okay, because of unbalance there were increased feudal losses, and since system was unbalanced, it was carrying neutral current also, so that was also taken care. Okay, I hope things are clear to you. Let us try to solve one more numerical problem. Example 2. I will read the problem first and then we will try to solve it. This is the example or problem. It says a three-phase, three-wire system. Now we have a three-phase, three-wire system is as shown below. I will give me some time. I will draw this three-phase, three-wire system. When it is three-phase, three-wire system, so there will be no neutral current. Three-phase voltages are balanced sinusoids with RMS value of 230 volts. That means the source voltages are three-phase, but they are balanced. Each RMS value of each phase voltage is 230 volts. So balanced set of three-phase voltages is applied to the load. The three-phase loads connected in star are given as ZA equal to 5 plus J12 ohms, ZB equal to 6 plus J8 ohms, and ZC equal to 12 minus J5 ohms. Compute the following. Part A, line currents IA, IB, IC and their instantaneous expressions. Part B, load active and reactive powers and power factor of each phase. And part C, various apparent powers and power factors based on them. Let me first of all draw the circuit diagram which is given in the problem. This is VAN. This is line current IA, while load is star connected load like this. It is given in the problem itself. This is the neutral of the load. This is VBN. This is IB. This is VAN. This is VBN. And this is VCN. And line current in line, this line C is IC. Okay, and this is three phase. This is the neutral, load neutral, and this is supply neutral. The two neutrals are not connected. It's a three-phase, three-wire system. This is load impedance ZA, this is load impedance ZB, and this is load impedance ZC. This is what we are given in the problem. So we have to find line currents. So part A is find line currents IA, IB, and IC. We have to find these currents. Now it may seem to you very easy to find IA. You may say that IA is VAN by ZA. It's not so. It's a three-phase, three-wire system. Neutrals are not connected. If you remember when we were discussing three-phase, three-wire system, I told you the voltage between, in three-phase, four-wire system. If you have a three-phase, four-wire system like this, and neutral is also connected. The neutral, load neutral and supply neutral voltage VN is always equal to 0 because the load neutral is connected to supply neutral. But in case of three-phase, three-wire system, the load neutral is not connected to supply neutral, and therefore there will be some amount of voltage between load neutral and supply neutral. So therefore your line current IA will not be VAN by ZA. It will be IA will be VAN minus neutral to neutral voltage by ZA. So therefore our first task is to find this neutral to neutral voltage. Okay, so we are given ZA equal to 5 plus J12 ohms. It is given in the problem itself. ZB, that's load impedance ZB, is also given 6 plus J8 ohms. So this is inductive, this is inductive, and ZC is 12 minus J5 ohms. It's capacitive nature. Anyway, we'll discuss it later on. So let us try to find out. And we are also given VAN is equal to 230 volts. It's 230 at an angle of 0 degree volts. VBN phasor is 230 at an angle of minus 120 degree volts. And VCN phasor is 230 at an angle of plus 120 degree volts. So this is a set of balanced three-phase voltages. RMS value of all the three-phase voltages is same, and this is the phase displacement minus and plus 120 degrees. So source voltages are balanced three-phase voltages. So therefore, if you try to find neutral to neutral voltage, which is very important. Here it will not be 0 because the two neutrals are not connected to each other. So VNN will be given by this formula, 1 by ZA plus 1 by ZB plus 1 by ZC into VAN by ZA plus VBN by ZB plus VCN by ZC. Actually, neutral to neutral voltage is given by total current into total, total impedance. So this is current in A, this is current in B, current in C, and these are the total impedances, load impedances. So therefore, if you apply this formula, you will get neutral to neutral voltage. Now, if you substitute the values here, so neutral to neutral voltage will be equal to, that is load neutral to supply neutral voltage will be equal to 1 divided by 1 by ZA. What is ZA? ZA is 5 plus J12 plus 1 by ZB. ZB is 6 plus J8 plus 1 by ZC. ZC is 12 minus J5 into VAN by ZA. VAN is 230 at an angle of 0 degree by ZA is again 5 plus J12 plus VBN by ZB. VBN is 230 at an angle of minus 120 degrees by ZB. ZB is 6 plus J8 plus VCN by ZC. VCN is 230 at an angle of plus 120 degrees by ZC. ZC is 12 minus J5. So this is it. So I am applying this formula there to find V and N. And if you apply the formula, these are in rectangular coordinates. You can transform them to polar coordinates, and then these are in rectangular coordinates. Transform them to polar coordinates, and then you calculate, and then you convert everything, transform everything into rectangular coordinates. So this will come out to be, let me tell you, this V and N will come out to be minus 94.22 minus J 123.18 volts, and this V and N will be under root of this square plus this square, okay, and finally this will come out to be 155.09 at an angle of minus 127.41 degree volts. So this square plus this square is 155.09 volts. And how do you get this angle? This tan inverse of imaginary part by real part, reactive part by real part, and that comes out to be this. Okay, so therefore your neutral voltage is very significant. It's not 0. Neutral to neutral voltage, it is 155.09 volts. Very significant value. So let us therefore find line currents. Let us find first line current IA. So what is your line current IA? It is VAN minus neutral to neutral voltage, VNN by ZA. So what is VAN? By the way, VAN is 230 at an angle of 0 degree minus VNN is this 155.09 at an angle of minus 127.41 degrees by ZA. ZA be how much is ZA? ZA is 5 plus J12. So you transform this also into polar, and now it's the job of calculator. Take your calculator in your hand and solve this. That will give you line current IA. As per my calculation, this line current comes out to be 26.67 at an angle of minus 46.56 degree amps. This is my line current IA. Please verify this figure. This is as per my calculation. But what about line current IB? That is VBN minus VNN by ZB. What is VBN? It is 230 at an angle of minus 120 degrees minus this VNN is 155.09 at an angle of minus 127.41 degrees by ZB. And how much was ZB? ZB was 6 plus J8 ohms. Load impedance ZB. So that will give, take calculator in your hand, transform these rectangular coordinates into polar coordinates, divide numerator with denominator, and then transform all the polar coordinate. Finally you will get something in polar form. Convert from polar form to rectangular form. So you will get IB, and you can retain that in rectangular form. In polar form. So IB will come out to be, as per my calculations, it is 7.88 at an angle of minus 158.43 degree amps. This is my IB. In a similar way, line current IC will be equal to VCN minus VNN by ZC. VCN is 230 at an angle of plus 120 degrees. Minus VNN is same, 155.09 at an angle of minus 127.41 degrees by ZC. And what is ZC? It is 12 minus J5. Solve it, you will find line current IC, and as per my calculations, line current IC is 24.85 at an angle of 116.3 degree amps. Now interestingly, you can see, although your source voltages were balanced, and there is no, but your load impedances are not balanced. Your load is not balanced. Because what is load impedance of, what is ZA? It is 5 plus J12 ohms. What is ZB? ZB is 6 plus J8 ohms. And what is ZC? ZC is 11 minus J5 ohms. So your load is unbalanced. And because of that unbalance in the load, you get unbalanced line currents. For example, the magnitude RMS value of line current IA is 26.67 at an angle of minus 46.56 degree amps. IB is 7.88 at an angle of minus 158.43 degree amps, and IC is 24.85 at an angle of 116.3 degree amps. So RMS value of IA is 26.67 amps, RMS value of IB is 7.88 amps, and RMS value of IC is 24.85 amps. So therefore your system becomes unbalanced. So this is also another example of unbalanced system, but we don't have neutral wire here. It's a three-phase, three-wire system. Okay, so once you have found these line currents, you are also in the problem, they ask you to compute the line currents and their instantaneous expressions. You have to write their instantaneous expressions also. Instantaneous expression of line A is IAT is equal to root 2 IA sine of omega t minus phi A. So IAT is equal to root 2 into IA. IA कितना है? अभी थोड़ी देर पहले हमने IA निकाला. IA is how much? 26.67. 26.67 sine of omega t minus, and what is phi A? Phi A भी हमने निकाला था. It is 46.56. 46.56 degrees. So IA is root 2 into 26.67 comes out to be 37.71 sine of omega t minus 46.56 degree. This is IA, mathematical expression for instantaneous value of IA. Similarly, you can find IB. IB, I have computed, it is 11.14 sine of omega t minus 158.43 degrees. And similarly, you can find IC. IC is 35.14 sine of omega t plus 116.3 degrees. So these are the expressions for instantaneous currents. Okay. So once you, that is about part A. This is what we are asked to calculate in part A. In part B, what you have to calculate? Load active and reactive powers and power factor of each phase. We have to find load active and reactive powers. Let us find apparent power of phase A, that is equal to voltage phasor into complex conjugate of current phasor. VA is 230 at an angle of 0 degree into current IA. Just few moments back we have computed that 26.67 at an angle of, if you remember, IA was 26.67 at an angle of minus 46.56 degrees. When you find its complex conjugate, magnitude will remain same, but phase angle will go from minus to plus. Here it is minus, here it will become plus 46.56 degree. Okay. इसको आप कंप्यूट कर लीजिए 230 into 26.67. This will come out to be 4218.03 plus J 445.6. Okay, so this into this कर लीजिए, वो पहले पोलर फॉर्म में निकलेगा, पोलर फॉर्म से फिर रेक्टेंगुलर फॉर्म में ट्रांसफॉर्म कर लीजिए. सो दिस इज द एक्सप्रेशन. Similarly, you can find SB. SB is VB into IB complex conjugate. VB is 230 at an angle of minus 120 degrees into IB कितना है 7.88 at an angle of 158.43 degrees. There it is minus 1 और complex conjugate से plus 158.43 degrees बन जाएगा. Let me write it clearly. 158.43 degrees. This into this, that will give you SB. This is SA. That will give you SB. SB comes out to be 1419.82 plus J 112.06. चलिए, उसके बाद apparent power of phase C is VC into complex conjugate of IC. VC is 230 at an angle of plus 120 degrees into IC. How much is IC? IC, as per my calculation, I have already calculated, IC is 24.85 amps at an angle of, there it was plus 116.3, complex conjugate से plus हो जाएगा 116.3 degrees. Okay, so SC इससे आपको मिलेगा, and I have calculated that as 5703.43 plus J 368.11. That's it. So this is apparent power of phase A, SA. SB is apparent power of phase B, and SC is apparent power of phase C. So therefore you can find real and reactive power separately. What is reactive? What is real power carried by phase A? That's the real part of this expression, that is 4218.03 watts. What is reactive power carried by phase A? That's the imaginary part of this expression, 455.6 watts. 445.6 watt. Similarly, PB is real part, that is 1490.82 watts, and QB is its imaginary part, 112.06 watts. Okay. Similarly, active power carried by phase C, that is this, is the real part of this expression, that is 5703.43 watts, and reactive power carried by this phase C is imaginary part of this expression, that is 368.11 watts. That's it. So real power, reactive power of phase A, real and reactive powers of phase B, real and reactive powers of phase C. तो ये हो गया. इसके बाद आपको in the problem you are asked to find each phase power factor. हर phase का अपना अपना power factor निकालना है अलग अलग. So what is the power factor of phase A? That is PA by SA. PA is 4218.03 by SA. SA है आपका 6136.3. तो इससे फेज ए का पावर फैक्टर निकलेगा. फेज ए का पावर फैक्टर आता है 0.6873. Similarly, you can find power factor of phase B, that is PB by SB. PB is, अभी हमने लिखा 1419.82 by what is SB, apparent power carried by phase B. वो थोड़ी देर पहले हमने निकाला. That is, anyway, I don't have that figure. You can find that. So this power factor comes out to be 0.7835. And similarly, power factor of phase C is PC by SC. PC is this, and SC is also, we have calculated few moments back, and this comes out to be 0.9979. तो ये आपके 3 phases के power factors है. That is about part B. Part C में what we are supposed to find various apparent powers and power factors based on them. अब हमें apparent powers निकालने हैं, like vector apparent power, I mean 3, ये तो individual था, अब vector apparent power निकालना है, that is under root of p square plus q square. What is p? P is pa plus pb plus pc, and q is qa plus qb plus qc. तो वो सारी figures आपके पास है. You just few minutes back we have calculated PA, we have calculated PB, we have calculated PC, that is real powers carried by the 3 phases, and we have also computed reactive powers carried by 3 phases, QA, QB, QC. इनको add कर लीजिए. So this will give you total active power of 3-phase system, and this will give you total reactive power of 3-phase system. Okay, उससे आपको vector apparent power पता चलेगा. So under root of p square plus q square will give you vector apparent power, and as per my calculation that comes out to be 12,807.78 VA. This is the vector apparent power. Okay. Arithmetic apparent power is SA plus SB plus SC. Now SA plus SB plus SC आप add कर लीजिए, figure is already with you, and the addition will give you arithmetic apparent power as 13,633.82 VA. Fine. उसके बाद effective apparent power आपको निकालना है, that is 3 VEIE. इस case में भी VE is same as V, that is 230 volts, and IE in this case will be equal to IEH तो होगा नहीं, it's a sinusoidal system, it will be under root of IA square plus IB square plus IC square by 3. I am not writing plus IN square because it's a 3-phase 3-wire system, since there is no neutral wire, so neutral current will be absent. So this will give you IE, and I have already calculated that as per my calculations, if you substitute IA here, IB here, IC here, so IA square under root of IA square plus IB square plus IC square by 3, as per my calculation that comes out to be 21.53 amperes. So therefore effective apparent power is 3 into VE, V is 230, into IE 21.53, or effective apparent power as per my calculation is 14,859 VA. Okay, so once you know these apparent powers, you can find the respective power factors. Vector apparent power is P by SV, and I have already calculated that comes out to be 0.8855. Arithmetic apparent power is P by arithmetic power factor is real power, 3-phase total 3-phase real power by arithmetic apparent power. And if you substitute the values are already computed few moments back, you can substitute them here, and comes out to be 0.83. And finally effective apparent power is P by SE. Substitute the values, and this comes out to be 0.73. Let me check the figures. 0.7632. 0.7632. Here also you can see effective power factor is lowest of all, and vector power factor is highest of all. Similarly, effective apparent power is highest of all. Effective apparent power is greater than arithmetic apparent power, greater than vector apparent power. Effective power factor is less than arithmetic power factor, less than vector power factor. So this problem also explains an unbalanced system and how to find these different types of apparent powers and corresponding power factors and their physical significance, their meaning. So I hope these 2 numerical problems will clear all your doubts. And with this, I will end my today's lecture. In this today's lecture, we have tried to solve a couple of numerical problems based on case 4. that is three-phase unbalanced non-sinusoidal system. Although we have taken sinusoidal system, but we have taken unbalanced system in both the numerical problems. First system was three-phase four-wire system. Second was three-phase three-wire system. Both systems were made unbalanced with the help of unbalanced load, and we have computed various types of apparent powers, vector apparent power, arithmetic apparent power, effective apparent power, and corresponding power factors, and try to understand what's the significance of them. Vector apparent power takes care of only the reactive power of the load. It does not take care of unbalanced or neutral power. Arithmetic apparent power, in addition to considering active power, reactive power, it also considers additional power loss caused by unbalance in the system. Additional power loss means additional power loss in the lines or in the feeder. And effective apparent power takes care of active power demand of load, reactive power demand of load, then unbalance, and in fact additional feeder losses because of unbalance, and also power which is flowing in the neutral conductor or neutral wire. So that's why effective apparent power will, you have seen in example 1, it's largest of all the three type of apparent powers, and effective power factor is smallest. So with this, I will end my today's lecture. So this completes our complete discussion on various cases. Case A we had discussed, that was three-phase sinusoidal balanced system. It was a balanced three-phase system. And we have seen that if the system is sinusoidal and balanced system, the instantaneous active and reactive powers are absolutely constant. That gives an advantage over single phase system, because in single phase system the instantaneous power is oscillating in nature, but three phase system instantaneous power is constant in magnitude, and that gives an advantage as far as three phase motors are concerned. That gives uniform pulsation free torque and smooth running of the motor. Okay, and then apparent power and power factor is calculated same way as we have calculated for single phase systems. Okay, there is nothing like vector apparent power, arithmetic apparent power, or effective apparent power, because system is sinusoidal, it is balanced also. So there is no unbalance, so no additional feeder losses. There are no harmonics, and therefore no neutral current. And since the system is balanced and sinusoidal, no neutral current is there. So you are, in this case, the effective apparent power, even if you calculate that, that will be same as arithmetic apparent power, that will be same as vector apparent power. Okay, and power factors will also be same. They will be equal. So that's why we don't define these terms in a three-phase balanced system. In a three-phase balanced system, just like single-phase system, we define apparent power, real power, reactive power, and power factor. And power factor is P by S, as you already know. That was case A. Case B was three-phase sinusoidal unbalanced system. Three-phase sinusoidal unbalanced system. System is still sinusoidal. The voltages and currents are not they are not having any harmonics. They are distortion free, but system becomes unbalanced. As soon as system becomes unbalanced, your equations, instantaneous power, active power, instantaneous reactive power, equations change altogether. You get totally different set of equations. And your instantaneous active power and instantaneous reactive power is no longer pulsation free. They have pulsations again. Whereas in case of balanced system, the instantaneous active power, reactive power, they were constant. Here it is not constant. Here the instantaneous active power, because of unbalance in the three-phase system, they will have oscillations. So therefore, whatever advantage was there in a balanced three-phase system, that advantage is lost here. Okay, and to take care of, because of another thing is that because of unbalanced system, there will be additional feeder losses, and we had taken one numerical example, and there we proved that if the system becomes unbalanced, the feeder losses become double than that of balanced system. And to take care of or to account for those additional feeder losses, we, in addition to vector apparent power, we defined another type of apparent power, that is arithmetic apparent power. And we proved that arithmetic apparent power is greater than vector apparent power because this takes care of, or this takes account of additional feeder losses also because of unbalance in the system. Therefore, arithmetic power factor is less than vector power factor. That was case B. Then we studied case C. Case C was three-phase non-sinusoidal balanced system. Non-sinusoidal balanced system. The system was balanced, but it was non-sinusoidal. There was distortion in voltages as well as currents. There was distortion in the voltages, and distortion in currents was because of distortion in voltages and also because of non-linear load. And we got different set of equations for instantaneous power and both active and reactive powers. And we considered three-phase, three-wire system, then three-phase, four-wire system. In case of three-phase, four-wire system, we have seen that neutral carries the current because of third and triplen harmonics. There are third and triplen harmonic currents which add up and flow in neutral wire. So therefore, in addition to vector apparent power and arithmetic apparent power, a third type of apparent power was defined, that was called effective apparent power, that takes care of additional power loss or additional power which is carried by the neutral because of the flow of third and triplen harmonic currents in the neutral. And we found that effective apparent power is greater than arithmetic apparent power, greater than vector apparent power, and effective power factor therefore is less than arithmetic power factor, less than vector power factor. And finally, over last 2 to 3 lectures, we discussed, or last 2 lectures of course, we discussed fourth case, the worst type of power quality, where your system is non-sinusoidal as well as unbalanced. Three-phase non-sinusoidal, unbalanced system. And we got set of equations for active power in all the 3 phases, reactive power in all the 3 phases, total active power, total reactive power, and again we found that effective apparent power is greater than arithmetic apparent power, greater than vector apparent power, and hence the corresponding power factor, effective power factor, is less than arithmetic power factor, less than vector power factor. Because of non-sinusoidal source, there will be neutral current. Because of unbalance in the system, it will cause neutral current, increased neutral current, and it will also cause additional feeder losses, which are taken care of by these types of apparent powers. And then three-phase, three-wire system was also discussed, and there also we calculated these type of apparent powers. And this whatever analysis was done by us in last lecture, that was aided by a couple of numerical problems which we tried to solve in today's lecture. And in fact, this is the worst type of power quality problem. If your system is for case B, case A, in case A, three-phase sinusoidal balanced system, there is no power quality issue. System is sinusoidal as well as balanced. Then cases B, C, and D, they there we have done the analysis for different type of power quality problems. Like case B was sinusoidal, three-phase sinusoidal, but unbalanced system. Unbalance in the system is a power quality problem. Case C, system was non-sinusoidal but balanced. Since the system was non-sinusoidal, it is a power quality problem. And case D, the system, three-phase system, is non-sinusoidal as well as balanced. So this is the worst type of power quality problem that we may face. And in today's era, we face these type of problems. Our three-phase systems sometimes are non-sinusoidal as well as unbalanced. So we have done the complete analysis, aided by 2 numerical examples, numerical problems, to clear our concepts. So this completes our discussions on various types of three-phase, single-phase systems, the power quality problems, and three-phase systems with power quality problems. We have taken 4 cases in three-phase systems, discussed and analyzed various types of power quality problems. Inshallah, from next lecture onwards, we will go for compensation of these power quality problems. We will discuss how to compensate for these different types of power quality problems. What are the various techniques available? With this, I will end my today's lecture. I advise all of you to go through this lecture and other lectures. And in case of any difficulty, please get connected to me. I wish all the best to all of you. Thank you.